Hello, everybody. Welcome to today's current seminar. Today we have two speakers, two talks. Our first speaker is Zhi-Feng Wei. He will be giving a talk on efficient transformer-inspired variants of physics-informed deep operator networks. Dr. Zhi-Feng Wei is a postdoctoral researcher at Pacific Northwest National Laboratory. He received his PhD in mathematics from Indiana University in 2024 with a minor in statistics. His current research focuses on scientific machine learning for partial differential equations. With that short introduction, the floor is yours and you can start your presentation.
Yeah, thank you. Thank you, Naz. Thank you, everyone. It's my pleasure to give a talk about my research. I'm happy to share with you about my work on efficient variants of DeepONet, inspired by the transformer architecture. This work explores how ideas from the transformer architecture can help us design more efficient and physics-aligned operator networks. Let's start with a bit of background on operator learning and deep operator networks. In traditional numerical PDE solvers, we compute one solution at a time. For instance, if we are given one initial condition, we run a simulation and obtain the corresponding solution. But in many practical applications, we need to solve the PDE for many different inputs. For instance, if we have a series of initial or boundary conditions, but in this case, we will need to repeat the solution process repeatedly. But doing this repeatedly could be extremely expensive for traditional PDE numerical solvers. So instead of solving the PDE repeatedly, we can think in a different way. We can learn the mapping from the initial condition to the solution directly using machine learning techniques. This idea is known as operator learning. In operator learning, using neural networks, we directly approximate the mapping from the input function to the entire function. Among different operator learning architectures, one of the most influential and widely used frameworks is the deep operator network, or DeepONet. In DeepONet, the input function, for example, the initial condition of a PDE, is processed by the branch net. This branch net is processing the input function, and the evaluation point where we want to compute the solution goes into the trunk net. And the final prediction is given by the inner product of the two outputs. As the first model that made operator learning truly practical, the DeepONet architecture was introduced by Professor Lulu and his collaborators in 2019. This paper, published in Nature Machine Intelligence, established the foundation for modern data-driven operator learning. The original DeepONet is purely data-driven. It learns directly from pairs of input and output functions. For example, from an initial condition and its corresponding PDE solution. And the PDE solution is typically generated by numerical PDE solvers. In other words, it tries to approximate the underlying solution operator purely from training data. However, generating large data sets of PDE solutions could be very expensive, especially systems. So in order to avoid the reliance on paired training data, the physics-informed DeepONet incorporates the given PDE directly into its loss function. Since the model output in machine learning is usually differentiable with respect to its inputs, so we can use automatic differentiation to compute the PDE residuals. This residual, together with with the loss on initial and boundary conditions ensures that after training, the model output will satisfy the physical law described by the PDE. The physics-informed DeepONet was proposed by Professor Paris and his collaborators in 2021. This article was published in Science Advances. Then, in the same year, 2021, an improved version called the modified DeepONet was proposed by Professor Paris and his collaborators. The modified DeepONet retains the vanilla DeepONet as a backbone, but it introduces two additional encoders, one encoder here and another encoder here. These encoders helps to improve the interaction between the branch and trunk networks. It preprocesses the inputs before the forward pass of the whole model. Therefore, it allows a richer interaction and better representation of the complex networks. Compared to the vanilla DeepONet, the modified DeepONet introduces interaction between the branch and trunk networks through these two encoders. This allows information to flow both ways, making the model more expressive and improving prediction accuracy across different PD problems. Here we can see some quantitative comparison of the vanilla DeepONet and the modified DeepONet. For the advection equation, the vanilla DeepONet reaches about 2% relative error. But the modified DeepONet reduces it to below 1%, although each training iteration takes more than 2 times longer. For the Burgers equation, we observe a similar pattern. The modified DeepONet achieves about 6 times lower error, again with a higher computational cost. So overall, we say trade-off clearly. Higher accuracy comes with a higher computational cost. So far, the modified DeepONet improves accuracy by strengthening the interaction between the branch and trunk networks, but it also increases the computational cost. This motivates us to look for a new design, a design that keeps the model efficient while enabling richer interaction and gives better accuracy. For this, we draw inspiration from the transformer attention architecture. Again, here is the structure of the vanilla DeepONet. The branch network processes the input function, for example, the input initial condition of a PDE, and the trunk network encodes the spatial location where we want to evaluate the solution. These two features are simply combined by an inner product. We can think of this as the trunk net providing basis functions and the branch net providing coefficients for combining them into the final output. This design of vanilla DeepONet is elegant and simple. So training the vanilla DeepONet is super efficient, but it is also somewhat limited. There is no deep interaction between the branch and trunk features, and this would restrict how expressive the model could be. Well, in contrast, the attention mechanism in transformers introduces a dynamic dependency. In attention, the output is given by a weighted sum of the value vectors, and the weights are the attention scores. The value vectors coming from linear transformation of the context tokens. And the combining coefficients, or we call it the attention score, are computed from the compatibility between the query and K vectors. And the coefficients, they change dynamically for each query token. We looked at the architecture of vanilla DeepONet and attention. Both of them can be viewed as forming an output by combining a set of basis functions with certain coefficients. But the key difference lies in how these coefficients are determined. In the vanilla DeepONet, the coefficients depend only on the context function, like the input condition, and they remain fixed for all query points. In contrast, in attention, the coefficients are adaptive. They depend on both the context and the current query. So the model dynamically reweights the basis functions for each query token or query point. Similarly, the context input in DeepONet only affects the coefficients, but in attention, the context interacts with both the coefficients and the basis. This forms a richer and bidirectional dependency in the model. These observations highlights a fundamental limitation of the vanilla DeepONet. The coefficients are static. They don't change with the query point, and the branch and trunk networks play completely separate roles. This may limit how expressive the model could be when dealing with complex operator mapping. In order to address these limitations, we introduce a transformer-inspired design where the coefficients become query dependent and the branch and trunk networks are dynamically coupled. Our goal is to bring this kind of dynamic interaction into DeepONet, but without fundamentally changing its elegant and simple structure. We aim for a non-intrusive modification, something that is lightweight and keeps the branch trunk design of DeepONet. This will also allow them to communicate dynamically. Here is a summary of the different architectural variants we explored. In our study, we considered time-dependent PDEs, so the query points have time coordinate t and space coordinate x. Each variant modifies how the branch and trunk networks interact. In other words, what kind of information each side can use. For the vanilla and modified DeepONet, they only use the input function u in the branch and space-time coordinate t and x in the trunk. The transformer-inspired variants progressively introduce cross-conditioning. For example, it allows the branch to also access spatial coordinates of the query point, which is x, or letting the trunk receive input function information or its Fourier coefficients. For different variant, we have different combinations as summarized in this table. Here in the table, u is the input function. U of x is the value of the input function u at the query spatial coordinate x, and this u hat is some leading Fourier coefficients of the input function u. To get a better idea of these variants, let's look at this variant called bx. In this variant, the branch network can say the spatial coordinate x of the query point. So we simply call it as b for branch, x for x. So it is called bx. This is different from the vanilla DeepONet, and it effectively creates some query-dependent coefficients. So far, we have seen how we can enable cross-conditioning in DeepONet by giving additional inputs to the branch and trunk networks, inspired by the attention mechanism in transformers. Now, let's take a closer look at three representative examples and say what their architectures actually look like. In the TL variant, the branch network processes the input function U as usual. The trunk network, however, takes not only the query point Tx, but also the local value U of x. This means the input function U now influences both the branch and trunk networks, establishing a bidirectional dependency between the branch and trunk net. Then in this variant called BXTJ, the branch network takes both the input function U and the spatial coordinate x, while the trunk network receives the query point Tx together with the entire input function U. As a result, the coefficients are no longer just determined by U. They also depend on the query coordinate x. And the input function U in this variant influences both sides, the branch and trunk. This forms a strong bidirectional dependency between them. Then in this variant called TF, the branch network still processes the input function U. The trunk network, however, now takes not only the query point T and X, but also the truncated Fourier coefficients of the input function. These coefficients provide a global frequency-based summary of the input function U. This is especially useful when the PDE has periodic boundary conditions. So this design allows the trunk network to be context aware. It can generate basis functions that depend on both query point and the global information of the input function. Okay, so far we have discussed the motivation and architectures. Next, let's say how these designs perform on real PDE benchmarks. We tested the DeepONet and its variants on several PDE problems.
Zhi-Feng, can I ask you a question?
Yes, please.
So you call it Transformer-inspired, just from the non-locality of the, right? But you don't actually do the QV in the product, right?
No, technically we don't do QV and K, but we are learning from their dependency.
Right. So you have more dependencies from one to the other, because we also, there was another, you didn't review it, there's another another paper we published in Crunch, Ahmad Pavan, called Fusion DeepONet, where we it's like one directional, not bidirectional, but basically the trunk links with the branch links with the trunk at every layer, and that turns out to be excellent neural network. So without the bidirectional, so I was wondering if you also consider just a one directional dependence.
Yes, that's a good question. I think we are currently working on a variant to include QK and V in the model, but in this work, we want to make the whole model lightweight, and we want to keep the efficiency of vanilla DeepONet to make it quicker. Because if we use the transformer attention module, it will be kind of slower in training.
George, also what you mentioned as a fusion reminds me of what the modified DeepONet does, where every layer of the trunk and the branch talk to one another.
Yeah, in the modified, they have also the trunk talks to the branch through the encoder.
Right. But I'm saying if you have even unidirectional at every layer, it goes more towards the modified DeepONet, and we wanted to avoid intruding inside the hidden layers. We want it to stay as simple as possible, like Zhi-Feng said.
Right. Okay.
Yeah.
Yeah, sure.
Thank you.
Thank you. Okay, I think we can now proceed to some results, including our results on viscous Burgers equation, advection equation, and KdV equation. Okay, first, let's look at Burgers equation with viscosity 10 to minus 3. In this PDE, we'll consider periodic boundary condition, and the initial conditions are sampled from a Gaussian random field. We have trained the vanilla DeepONet, the modified DeepONet, and all variants to solve Burgers equation with viscosity 10 to minus 3. This picture shows the relative L2 error versus the training time. Here we have different markers for different variants, and the x-axis is the average per iteration training time ratio relative to the modified DeepONet, and y-axis is the mean L2 relative error on the test dataset.
Zhi-Feng, quick note, these are all physics informed, right?
Oh yeah, they are all physics informed.
They're not data-driven DeepONet, all physics informed.
Yeah, they are all physics informed.
Okay, yeah.
Thank you. Okay. So as we can say, this marker, this black star, stands for the modified DeepONet. Its ratio to itself is always 1. And all the variants are shifted to the left of the modified DeepONet. This indicates a substantial reduction in per iteration time cost. For instance, for this marker here, its training time per iteration is only 60% compared to the modified DeepONet. This improvement in efficiency is due to the simple architecture of our variants inherited from the vanilla DeepONet. We can also say this golden marker, it stands for the variant TF. It gives similar predictive accuracy as the modified DeepONet at almost less than half training cost. And for the variant TF, marked as the golden marker just now, we can also compare the convergence of the mean L2 relative error with respect to the wall clock training time. In this plot, the blue curve is the modified DeepONet, and the green curve is the Transformer-inspired variant TF. In this representative draw, the variant TF achieves its final mean L2 relative error of around 1% in 2,500 seconds. But for the modified DeepONet, it attains the same level of accuracy for more than 5,000 seconds. This comparison reveals the efficiency of variant TF. In order to get a more complete picture, we may look at the violin plot of the relative L2 error distribution over all test cases. From this plot, we can say that the variant TF has similar performance as the modified DeepONet. They have similar meaning as indicated by the red dot, and they also have similar quantiles as indicated by the blue lines. Their distributions are also pretty similar to each other. Now we can say from the data plot, from the plot we saw in the previous page and this violin plot, that the variant TF has a similar performance as the modified DeepONet. But can we assert equivalence in performance using rigorous statistical methods? The answer is yes. In order to check whether the two models, the variant TF and modified DeepONet, are statistically distinguishable in accuracy, we did Wilcoxon test on the sequences of relative L2 error given by the variant TF and the modified DeepONet. The result confirms that the two sequences are statistically equivalent. In other words, Wilcoxon test tells us the variant TF gives predictive accuracy statistically equivalent to that by the modified DeepONet. This method, Wilcoxon Two One-Sided Test, is a method from statistics. I don't think we have enough time to delve into the details, but in our preprint, we have a section in the appendix mentioning some details and explanation about this method. In order to further test the behavioral similarity between the variant TF and the modified DeepONet, we calculated the Spearman's rho. This quantity is calculated at the correlation coefficient of the ranking of the error sequences given by the variant TF and the modified DeepONet. Spearman's rho as a correlation coefficient is a number between -1 to 1. Usually, a higher positive rho indicates that the models tend to perform well or poorly on the same test cases. Therefore, a higher positive value of rho suggests similar underlying behavior of the two models. For Berkeley's equation with viscosity 10 to -3, the Spearman's rho is 0.869. This value is pretty high, so the error patterns of variant TF and the modified DeepONet is pretty similar. Well, as we can say from the experimental results, the variant TF gives a similar predictive accuracy at reduced training cost. But why this variant works the best? Why it is better than other variants? Well, we first recall in variant TF, we added several leading Fourier coefficients to the trunk net. And in
how many, Zhi-Feng? How many?
Yeah, good question. This depends on I calculated
for this viscosity, just for this viscosity, how many did you do for this viscosity?
It is 7, the first 7.
7, okay, thank you.
Yeah, for different viscosities like 10 to -2, I use 5, and for 10 to -4, I use 9.
Thank you.
Yeah. Okay. And in viscous Berkeley's equation, the dynamics are primarily governed by low frequency Fourier modes of the initial condition, while in higher frequency components are rapidly dampened by the viscosity. Therefore, we can anticipate including the leading Fourier coefficients of the initial condition into the trunk net effectively introduces a low-pass filter, emphasizing the dominant low-frequency modes and discards high-frequency noise. The superior accuracy of variant TF is consistent with the underlying physics of viscous Berkeley's equation. That is viscosity 10 to -3. And now let's move on to Berkeley's equation with viscosity 10 to -2. Compared to the case of 10 to -3, the dynamics here would be smoother because diffusion plays a stronger role. We use the same setup, a periodic boundary condition, and the initial conditions are still sampled from a Gaussian random field. And for Berkeley's equation with viscosity 10 to -2, we also compared different variants. We can say with reduced training cost, the best variant TF, this golden marker, still gives comparable accuracy with similar to the modified DeepONet, but with a much lower training cost. Again, efficiency here is due to the simple architecture of all variants inherited from the vanilla DeepONet. In this case, For variant TF, we also compared the convergence of mean L to relative error with respect to the wall clock training time. Still, in this picture, the blue curve is for the modified DeepONet, and the green curve is for the variant TF. In this representative ROM, the variant TF achieves its final mean L to relative error of 0.2% in around 3,000 seconds. But for the modified DeepONet, it attains the same level of accuracy for more than for more than 5,000 seconds. Again, this comparison reveals the efficiency of the variant. We again look at the violin plot of the distribution of the relative L to errors over all test cases. The overall patterns are still pretty similar. We can say the predictive accuracy of the modified DeepONet is slightly better than the variant TF because the violin has a lower position in this plot. Again, we want to use Wilcoxon, and we found that the two error sequences are not statistically equivalent as shown in the violin plot. In this case, the variant TF has a compromise on accuracy. In order to check how big this compromise is, we use a statistic called glass delta. This value is 0.397. This indicates a modest compromise in predictive accuracy. Therefore, at the cost of a modest compromise in accuracy, we gain a big improvement in efficiency. I think this trade-off is acceptable. And for Borgen's equation with viscosity 10 to minus 2, the Spearman's rho between TF and modified DeepONet is still pretty high. It is 0.858. So the error patterns of variant TF and the modified DeepONet are still pretty similar. In summary, for viscosity 10 to minus 2, the variant TF offers a good efficiency and accuracy balance. This is consistent with our earlier observation. Okay, now let's move on to advection equation. The initial and boundary conditions are given, and the advection velocity is sampled from a Gaussian random field. For advection equation, different variants are compared in this picture. Still, we have this black star for the modified DeepONet and this golden marker for the best variant, BXTG. With reduced training cost, we can say the best variant BXTG gives predictive accuracy comparable to the modified DeepONet. Again, all the variants are pretty efficient. And this efficiency is due to the simple architecture inherited from the vanilla DeepONet. For variant BXTG, we also compared the convergence of the mean L to relative error with respect to the wall clock training time. In this representative ROM, still the green is for the variant.
Zhi-Feng, can you remind us what is BXTG? There's too many acronyms.
We insert X to the branch net and the whole sequence of the input function to the trunk.
Yeah. Thank you.
G means global.
G global, yeah.
Yeah, thank you. Yeah. We have this green curve for BXTG and the blue curve for the modified DeepONet. In this representative ROM, the variant BXTG achieves its final mean L to relative error of about 0.9% in around 3,000 seconds. But the modified DeepONet attains a similar level of final accuracy for 4,400 seconds. This comparison reveals the efficiency of the variant BXTG. Well, again, we want to look at the violin plots of the distribution of the L2 relative errors over all test cases. We can say the error distribution of DXCG is pretty similar to that of the modified DeepONet. Again, we want to use Wilcoxon test. And in this case, we found that the two error sequences given by BXCG variant and the modified DeepONet are statistically equivalent. For advection equation, the Spearman's rho is super high. It is almost 1. So the error patterns of variant BXCG and the modified DeepONet are rather similar. In summary, for advection equation, variant BXCG offers a similar predictive accuracy at a reduced training cost. As we can see from the results, the variant BXCG offers good accuracy at a reduced computational cost. But why this variant works well for advection equation? In fact, we first recall the variant BXCG, we added the 4 input function u to the trunk. And the input function u in this equation is the velocity field. And in advection equation, the solution is determined by the transport of initial data along characteristic defined by dx dt equals u of x. Therefore, the global encoding of the velocity field enhances the model's ability to resolve directional propagation patterns. Therefore, the predictive accuracy could be improved. And the superior accuracy of variant BXTG for advection equation is consistent with the underlying physics. Now let's move to KdV equation. The initial condition for KdV is simpler for this equation. Here, u of x, the initial condition, equals a times sine of x plus b cosine of x. And a and b are standard normal variables. We consider a periodic boundary condition for KdV, and the dispersive coefficient delta equals 0.1. For KdV equation, the different variants are compared in this picture. Still, we have this black star for the modified DeepONet, and this golden marker for the best variant, BXCJ in this case. We can say from the picture, the best variant BXTJ gives predictive accuracy better than the modified DeepONet and with much less training cost. The per iteration training time for BXTJ is only 2/5 of that for the modified DeepONet. Again, this efficiency is due to the simple architecture of the variants inherited from the vanilla DeepONet. And for variant BXTJ, we also compared the convergence of the mean L2 relative error with respect to the wall clock training time. Still, we have the blue curve for the modified DeepONet and the green curve for the variant BXTJ. In this representative ROM, the variant BXTJ achieves a lower error within a shorter training time. In fact, as we mentioned just now, the training time of variant BXTJ is only 2/5 of the modified DeepONet. This reveals the efficiency of the variant again. All right, we again look at the violin plot of the distribution of L2 relative errors over all test cases. The variant BXTJ and the modified DeepONet have a similar error distribution. Both models give low median error and low quantiles, as indicated by the red dot and the blue lines. But there are also some big errors in both models. As suggested by the volume plot, as we mentioned, a small number of test cases have relatively large errors for both BXTG and the modified DeepONet. A close inspection reveals that the errors are highly localized in regions of spacetime where the exact solution has large gradients. This could be hard for both models. So for those test cases, the errors could be pretty large. Again, we used Wilcoxon and found the two error sequences given by variant BXTG and the modified DeepONet are not statistically equivalent. In this case, the variant BXTG gives better accuracy. For KDV, the Spearman throw is 0.86. This is still pretty high, and this indicates a strong positive correlation in the error patterns of the variant BXTG and the modified DeepONet. In summary, the KDV equation, variant BXTG offers a better predictive accuracy at a reduced training cost. As we can see from the experimental results, the variant BXTG offers better accuracy than the modified DeepONet at a reduced computational cost. Recall, in variant BXTG, we added X to the branch and the full input function U to the trunk. KDV equation is usually sensitive to the initial condition, so directly providing the entire initial condition to the trunk is likely to improve predictive accuracy. Okay, let me wrap up by summarizing the key ideas and what we see ahead. Inspired by transformers, inspired by the attention mechanism in transformer architecture, we designed several new variants of DeepONet that are simple, efficient, accurate, and physics aligned. They are simple because the modifications are non-intrusive. The core structure of DeepONet remains unchanged. They are efficient since these changes do not increase training time or computational cost compared to the vanilla DeepONet. They are accurate, achieving performance comparable to, and in some cases better than, the modified DeepONet. And finally, they are physics aligned. Each PDE naturally favors the variant that best matches its underlying physics. Looking ahead, we want to rethink how the trunk net interacts with the input function. We have tried global inputs and pointwise inputs, but there is a middle ground. In physics, influence is often local. We can think of the domain of dependence in hyperbolic PDEs. So a natural next step is to localize cross-conditioning, where the trunk only sees a small neighborhood around the query point. This would give us the best of both worlds, the efficiency of DeepONet and the physical consistency of classical numerical solvers. That concludes my talk. Thank you for your attention. I will be happy to take any questions.
Thank you so much, Zhi-Feng. Now we open the floor for questions. Do we have any question for the speaker?
Hi, Zhi-Feng. So I'm Nikhil and I'm a PhD student in Crunch Group. I have a small question. So can you give some insight into what is your number of trainable variables in both the your transformer-inspired variant and the modified DeepONet? I was just wondering if they are comparable or same order, the number of trainable parameters. I don't know if I missed it.
I didn't mention this technical details in my slides, but yes, we want to compare them in a fair level. And in our experiment, we keep the variants and the modified DeepONet to have the same width of the neural network, and we also keep them to have the same depth. So in this way, they are compared in a fair way.
I see. So your computational time is in modified one is high because of the interaction, and you differentiate to that. Understood.
Yeah, that's right. Yeah, it makes sense.
All right. Thank
Yeah.
you.
Thank you
Nice
for a
talk.
good question.
Hi,
Yes, sir.
Zhi-Feng. Yeah, I'm Rutvik. I'm a first year PhD student at the Crunch Group. I had two questions. Yeah, first of all, great talk. I think it was very well placed and easy to follow.
Yeah.
So going back to one of those slides, like for example, when you were talking about the advection equation, or maybe specifically the Berger equation,
The advection equation, right?
yeah, like what I want to ask is we see that the best performing variant is kind of dependent on the problem that you are targeting, right? Like for example,
that's
in the
right.
Berger equation, you see that the variant TF seems to like consistently show best performance for like different values of the viscosity. But however, like when you move to different problems, like for the advection and for the KDV, you show that a different variant works better for the different problems, right? So
Yes.
what is the kind of intuition behind that, and how do you think we should be like choosing the variants depending on the problem that we are trying to solve?
Yes, that's a good question. I think as we saw, we have for different PDE, we have different best performing variant, and these variants are corresponding to the underlying physics of the PDE. So if we have for this PDEs, we did thorough test on all the variants. If we are given a new PDE, and I think I will first do a quick analyze about the physics of this PDE. What kind of information is the most necessary for the neural network to do computation? And after this analysis, I will try to emphasize this quantity in my neural network. And so in this way, we can get some idea about which variant to choose in our computation.
Right. Yeah, that makes sense. Thank you. So one follow-up on that, like for example, in the Berger equation question, I think you show for different viscosities that consistently the variant TF performs the best, right? Like I think you
yes. Yeah.
Right. So do you do a similar study for the KDV as well, like for varying the delta value and then seeing if the BXTG variant consistently performs the best?
For KDV equation, I have to say KDV is pretty hard. It's hard to solve.
Okay.
It's super
Right.
sensitive. So we only tried okay, it's here. We only tried this single value of delta in our experiment.
Right.
And the initial condition is also carefully chosen to make
Okay.
it not too easy, not too hard.
Right.
Yeah.
Okay, got it. So is your hypothesis that if delta value is something else, the BXTG variant would still be the best for the KDV equation? So what I'm trying to like get towards is irrespective of what the parameter value is, the variant that performs the best would consistently be the same for a given equation for a given PDE. Is that the case?
Yeah, that's a good question. First, let me tell you why I choose this value. I'm choosing this value because I want to make a fair comparison with some existing literature. They use delta equals 0.1, so I use it here too. For your second point, I think I can do more experiment to try more values of delta. I think if we try different delta, the result should be pretty similar. I have a confidence in the best performing variant.
Okay. Yep. Thank you.
Yeah. Actually, we also tested the variant TF for KDV equation as we saw here. But it's still pretty efficient, but its accuracy is not as good as this variant, as this golden variant, because for KDV equation, as I said, it's super sensitive to the initial condition. So the Fourier coefficients is not quite enough to provide enough information.
Right. So are you choosing the initial condition such that there is no soliton interaction happening in the future time steps?
I'm trying to make the problem hard, but not too hard.
Got it. Yeah. Okay. Thank you.
Yeah. Thank you.
Thank
for
you
the
so
question.
I think also Kamal has a question. George, do you want to go first or Kamal?
Yeah, let me finish my question.
Okay.
Continuation of Zhi-Feng, very good talk. I really enjoyed seeing the results and how different. What it is really, it's a balance between coupling and the type of a PD, and you could see even with a parabolic PD like the Berger's, as you make it more towards hyperbolic, it changes. The results are changing a little bit. But also, I like the way you introduce the statistical metrics for comparison. I think that's actually something that we should all use. But I would have liked to see perhaps two more variants of DeepONet there, namely the two-step DeepONet. In our experiments, whenever we run in trouble, we go to two-step DeepONet. Two-step DeepONet, I think it's the most accurate one. Not necessarily the most efficient, so it will be interesting to see. My guess will be that the two-step DeepONet, and there's also a physics-informed version of two-step DeepONet that Elham has developed. But the two-step DeepONet would be, in terms of the accuracy, probably beat everyone. But in terms of the cost, it would be between your method and the modified method, somewhere in the middle, around zero point 0.5, for example, there, something like that, because it is expensive. But it does. So that's one version, the two-step DeepONet, because we use it a lot. And then the other one, which one I already mentioned, the one-way interaction, namely the fusion. It's called fusion DeepONet, because we have used fusion DeepONet for discontinuous problems, fracture, for shocks, and also for geometry encoding. So, I mean, of course, there are many variants, but I'm just telling you the ones that we practitioners use in real problems, including industry. So these are the two problems these are the two methods we currently use pretty much. If you can add that in your map. And another one, what I would also add is maybe a 3D Helmholtz equation, a stationary equation in high dimensions to see how all this fare. For example, yeah, I mean that's sort of a good. So
Thank you.
yeah, Varun, I think Varun, what paper? That's a fusion paper. Varun put a fusion DeepONet paper that he's a co-author. So on the chat, so you can look at it. But it's really interesting. I'm not crazy about the title, although actually the observation that you made looks very nice. What it's here, more mathematical, it's not like the transform. Is really the coupling that. What is the amount of coupling that we need between the branch and the trunk? And I think your paper brings this to really gives you good ideas of what's happening. If you add a few more cases, you will populate the landscape, so to speak. So it will be extremely useful. Uh, of course, the observation with the analogy with transformer is good, but it has to do with the non-locality and the coupling, really. Yeah. But thank you very much. It was an excellent talk. I enjoyed.
Yeah, thank you. Thank you, George.
Yeah, thank you. Okay, Kamal is next, and
Can I just add a quick thing?
sure.
Yes.
Yes.
So the reason why we went with title that involved transformers was because it was indeed inspired by transformers because of the non-locality. But you're right that there are the landscape is much richer, so it doesn't have to be just inspired by transformers. You could have all sorts of other coupling ways to do the coupling. But I also want to go back to what Ruthwick asked. Our hope is that we can create a kind of dictionary between physics and conditioning for DeepONet, so that if you have a new problem where you have the equations, you can do some kind of analysis to see which term dominates, and then you can try maybe the variant first that respects this particular term, this particular physics, and then go from there. in the same way that in finite differences, let's say you have certain schemes that are better for hyperbolic problems, parabolic problems, etc. Yeah. Thank you.
Hi, I'm
Thank you.
Kamal. I have two questions actually. I think few of the slides you showed the filing plot. So some of the cases, the filing plot for the transformer-inspired it has a long tail than the modified one. Is it like
For this one,
less generalizable? Yes, like is it less generalizable than the modified one? Did you test outside distribution anything?
well, yes, that's a good question. When I look at this violin plot, for the overall shape, they look kind of similar, but it has a bigger tail. It was not surprising for me because the biggest value is still within the range. So we have around 1.9 here, and it is 1.7 here. So it's not a big difference.
Yeah.
But of course, we can look into these hard cases for the variant to get more idea. Yeah, I think that's a good question. I will look into it.
Okay. The second question I have regarding the memory, like, is it required more memory in the transformer?
You mean for the variants?
Yeah, like the transformer-inspired required more memory than the vanilla DeepONet.
Well, usually, in my experiments, the memory is never a problem. We are working on a H100 chip, on a H100 GPU, and we are doing all the experiments in JAX, and it's always pretty quick. It's not a problem. For usually, if you have to compute, if you have to care about the memory, I would say all the variants are cheaper in memory than modified DeepONet because in modified DeepONet it needs more memory to deal with the interaction brought by the encoders.
Like why I'm asking actually because like if we have a large data set, we might have to go for smaller batch size. If you have a memory issue, that time the timing may increase.
In our experiment, the batch size is always 10,000.
Okay.
So it's not a problem there. Memory is not a problem. It could be, at the very beginning, I tried PyTorch, but I want to make it quicker, so I turned to JAX, which is really quicker. So it's the memory is not a problem.
Okay. Thank you. Thank you.
Thank you so much. And also, I think Varun put another link for GitHub. Okay. Zhanzhang, do you have questions?
Yeah, I have a very quick question. I'm a postdoc here. My name is Junja. It's a very great talk. I just want to make sure the physics informed part. Is that a pure physics informed, or you also need some labeled data for the output?
No, we don't need no label data is needed.
Okay, so pure physics informed. Okay,
Yeah.
thank you.
Yeah. Thank you so much. I think it's time to close this session and move to our second session. Thank you so much, Zhi-Feng, for your great talk.
Thank you.
So our second speaker is here. Hi, Zhu, can you hear me?
Yeah, I think I'm already sharing the screen. Can you see the screen?
Thank you. Yes, thank you so much. Our second speaker is Dr. Haishu Wu. He will be giving a talk on from RoPINNs to ProPINNs, improve optimization architecture towards practical neural PDE solvers. Haishu Wu is a currently postdoc fellow at MIT CSAIL, working with Professor Matosik. Previously, he received his PhD and bachelor's degree from Tsinghua University under the supervision of Professor Ming-Sheng Wang. His interests lie in scientific machine learning, especially physical world modeling and PDE solving. With that short introduction, the floor is yours, and you can start your presentation.
Okay. Hello, everyone. Thanks for introduction and organization. Actually, I really enjoyed the previous talk, and I have learned a lot. Okay, and my name is Haishu Wu. I graduated from Tsinghua University and currently a postdoc. Today, I will talk about some progress PINNs, and the talk title will neural PDE solvers, from RoPINN to ProPINN, improved optimization at that. I'm really excited to give this talk, especially as a home of PIN. Honestly speaking, because my main research field is machine learning instead of physics. So this talk may provide some new perspectives from the ML researchers and hope it can be interesting to you. I would like to start with some background. In the real world, there are some very interesting phenomena like the turbulence, atmosphere circulation, and stress. Long-standing and fundamental scientific question to understand the world. Because I'm from the machine learning community, a widely used and well-established approach is data-driven, which usually starts from intuition or computer vision. It means we can record this process as an image or videos using a camera or other types of sensors. After that, we can learn a vision model to approximate these dynamics. Like we can make some vision transformers for weather forecasting. And the above-mentioned approach works in this task. It's also named as world model by researchers, because world model is a kind of which concept in this area. Researchers will name these weather forecasting models also world model. However, current video models still struggle in modeling the physics like UL hallucination in the video generation models. So sometimes the generation results may not physically reliable. And if we think about this phenomena from a more basic view, we can find that these phenomena are inherently governed by scientific rules, and specifically extensive physics process in the real world can be precisely described as differential equations or that PDEs, as the Navier-Stokes equations for fluid dynamics and the stress-strain relations in fluid mechanics. Accurately solving these PDEs is really important, and not only for understanding the world, but it can support many engineering problems like and manufacturing. However, solving PDEs is a great challenge. The Korean Mathematics Institute listed the problem of Navier-Stokes existence and smoothness into 7 millennia in parallel with the PNP problem in computer science. So it's really hard and nearly impossible to obtain the analytic solution of PDEs. Fortunately, after decades of effort, we have very mature numerical methods, the finite element methods or methods. And these methods can solve PDEs very stable. May suffer from the huge computation cost. For example, if you want to simulate a car, maybe it may take 4 hours or days or months. And most of these methods rely on the approximated domain discretizations. Although some methods try to use some boundary element methods, they do not rely on the discretized computation mesh. But I don't think they are as popular as the EM or EM methods. And recently, some neural PDE solvers have been explored, which are either based on a pure data-driven model like DeepONet, or based on a pure physics-driven approach like PINs. The researchers attempt to utilize the learning capability and the auto-differential property of neural networks to build an efficient and precise surrogate tool. This is only a thing for current research. These neural networks still cannot make a sufficiently efficient and sufficiently precise surrogate tool for very mature numerical methods. And if you're talking more about the whole background, I think neural PDE solvers is not only a hot direction in the physics community, but also a booming direction in the ML community. Since 2024, about 2 years ago, every mainstream ML conference will have the special tutorials to this. I still remember the AI for differential equation workshop in ICLR 2024. The meeting room is so crowded, I even cannot enter the activity. And I also counted the number of papers by searching their titles based on the keywords. I surprisingly find that the papers about PDE or physics comparable to the world model. That is quite surprising because world model is a really hot topic in AI ML community. So I think there is a rising attention in ML community on this area. And some neural PD solvers has already been used in simulation software such as SimAI in ANSYS and the Physics AI in Autel. And here are two introduction videos to present how this type of software works. Basically, they are training a surrogate model based on several collected data, and then do the fast inference to help design. Okay, that is a brief review about the research background. Next, I will go back to the technical aspect. As mentioned by the Professor George, we can think about this problem from two axes. One is the data, and another is physics. Following this principle, we can roughly categorize the previous research on neural PD solvers into three parts. First is pure physics, and the representative work is physics-informed neural networks, named as PINs. Some researchers also name it as EM. I saw of these names in papers about 5 years ago, but actually I don't think. But I don't know why they call this as neural FEM. And in this talk, I will discuss the difference between the FEM and the PINs. The second is pure data. The representative work is neural operators, neural circuits. For this part, the physics are governed by the training data. The third will be the hybrid methods, as integrating neural networks into numerical methods, or introducing physics laws into neural operators, which is also known as physics-informed neural operators. Okay, today I will only focus on the first part, things. The basic idea is to enforce the output and the gradients in models to satisfy the target equation. More details, here is an example of the convection equation in one-dimensional time-dependent space. Here I will going to just introduce some basic knowledge, because this basic knowledge will relation about my work. Okay, to build a physics-informed neural network, we need to first sample some collocation points from the input domain. Then adopt the spatial temporal coordinates of these points as the model inputs. Next, we can then calculate the PIN loss based on the model output and the gradient on these sampled collocation points. And the final loss can be informally formalized at the bottom. Minimizing this PIN loss, we can make the neural network gradually satisfy the target equation. Actually, after reading this paper, I'm completely attracted by the proposed elegant formalization, which utilizes the auto-differential gradient, and is without domain discretization, and also ensures the explicit constraint. However, despite such a beautiful definition, previous researchers also noticed that PIN model still have some underlying issues to be solved. From the experiment practice, researchers found that PIN may fail in some quite simple tasks, equations, reaction diffusion equations. So here, the left part is a ground truth solution, and the right part is a PIN solution. Because the solution field is quite smooth and seems easy to fit for a neural network, PIN still present the failure mode. They cannot catch up the errors in the field. The paper make a detailed investigation of the parameter beta in the convection equation. From left to right, they kept increasing the beta value and recorded the loss landscape change. Based on the detailed experiments, the paper identifies the problem as hard to optimize the loss. You can also find many sharp corners in the landscape. It indicates that due to the spatially defined gradient-dependent loss, PIN may suffer from some optimization issues. And actually, optimization is a very long-standing problem in the mainstream deep learning models. For example, before ResNet, the community finds that it was really hard to train a model with over 10 layers. So if you keep increasing the layer numbers, performance will getting worse and worse. And this situation is quite similar to current PINs. It's quite unstable to train PINs with many layers, at least to my best knowledge. Even today, it's really hard to ensure a stable optimization for large language models. That is why people are quite surprised when DeepSeek V3 states their training process not has any loss spike. That's 2 years ago when I started my research. PINs, I choose to begin with the optimization aspect. And the first work is RoPINN, region-optimized physics-informed neural networks, which was published as a poster paper in NeurIPS 2024. Okay, in this paper, we rethinking the formalization of pins, and notice that there are two hidden limitations. First, the pin loss is defined at the collocation points. The model is expected to generalize to the whole input domain, which is a mismatch. And secondly, although we can configure the loss exactly following the equation definition, it still is still insufficient because the equation actually indicates an infinite order constraint. For example, for the convection equation shown here, we can take a derivative on x for both sides of the equation. Then we can obtain a new equation with higher order. However, the vanilla pin loss does not consider this. And the previous works has tried to end the higher order regularization to enhance the equation satisfaction, which will end a higher order constraint in the loss like this. However, this may cause a huge computation cost to calculate the higher order derivatives, sometimes unstable. And regarding the GPU memory cost, I think it's fine because the current pin model is still very small. If you try something like a transformer with many layers, it's really hard to calculate such derivatives from the output with respect to the input. And in that paper, we propose a new paradigm for training pins, which is region optimization. So the key idea is quite simple, which is to extend the optimization process of the scattered points like this into their regions like this. Let's say the region is omega r, where r is the region size. It's highlighted in the red. Loss term in region optimization is based on the region integral, which is different from the previous sum-based scatter definition. Next, I will show why this paradigm is better than optimization and how to efficiently implement this completely new framework. We analyze the generalization bound in expectation, which measures the difference between the training loss, this is the training loss, the error of the entire input domain. Actually, most of deep learning theories based on the generalization that this is a very convenient tool to analyze the performance of different models. And here are some basic assumptions. The following theorems are based on the Lipschitz constant and the smoothness of the loss function, which coefficient is denoted. And in fact, the generalization of point optimization has been widely explored. And the generalization error can be bounded by the Lipschitz constant loss function. And in this paper, we newly built a theoretical framework for region optimization. We theoretically prove that introducing the region, which is omega r, linearly decrease the generalization. Under this theoretical framework, we can find that the canonical point optimization and the globally sampling collocation points, two extreme cases, especially for the second case, which is actually sampling all the points in the input domain. So it's equivalent to directly optimizing the loss defined on omega. This line is very ideal, but it's not applicable in practice because it requires the calculation, the whole integral on omega. So based on the above theoretical results, we design a practical
Can I ask
algorithm.
a question here before this?
Yeah, of course.
So if you go back, so the subdomains are disjoint regions, right? You don't overlap them. You don't overlap them in any way, do you?
Actually, we do not care about this. You can overlap that. And the theoretical analysis here is actually a simplified equation. So we also provide an overlapped case. And there is a more complex theory in our paper, but we don't show here. And in practice, we don't care about if they are overlapped or not. We just turn the region size as a parameter automatically. Yeah.
And you also don't resample. In other words, every subdomain remains the same throughout all the epochs. Am I right?
Yeah, actually, we will resample different points at different iterations.
Or you resample. So every
Yes.
subdomain, the subdomains will have different points at every epoch, or every so often.
Yes, every iteration actually.
Every
You can
iteration.
see that. You can also see that at the epoch.
Okay, thank you.
Yeah. So based on this theoretical result, we design a practical algorithm named as RoPINN, which can seamlessly implement the region optimization paradigm. So the algorithm contains two steps. The first is a Monte Carlo approximation. The second part is a trust region calibration strategy to ensure a more robust training. And for the first part, we adopted the Monte Carlo sampling to approximate the region integral. Actually, because we cannot sample all the points within a region because it's infinitely fine-grained, we can just do the sampling. But for efficiency, we propose a very efficient way to implement this. That is only sample one point in each region to every iteration. I think that is a question from Professor George. But it's worth noting that although we can only sample one point within each region, the whole training process contains hundreds of thousands of iterations. But the sampling coverage of each region is actually quite sufficient if we consider the whole training process. And we also prove that this design is equivalent to a high-order loss function like this. Just based on the Taylor expansion, we can obtain a higher order loss term. And I also want to highlight that the region sampling we adopted here is tailored to the special definition of PIN loss, since we can precisely calculate the loss at any sample point based on the PIN definition. That is why we can enable such random sampling among different iterations. And here is the convergence ratio analysis. We prove that such sampling can also enable the convergence.
Hi, Haishu. My name
Yeah.
is Juan. I'm a PhD student here at Brown. I have a question. I actually didn't follow that well. Can you please repeat again? So you're proposing a new sampling scheme, or how is the?
Yeah, you can just view this as a new sampling strategy. Like previous sampling, I have read some papers like RAR or RAG. They will define the sampling strategy based on the global criterion. Like they will change the sampling points in a global region within the omega R. And in this paper, we propose that do not determine which point to sample globally, just do a small perturbation for previous location points. Yeah, you can just view this strategy like this.
But if you're sampling, let's say enough points, like. Do you have to exactly constrain that as small perturbation? Because when you say small perturbation, what I maybe I'm not getting it right, but what I understand is like you take your point and then you displace it a little bit to the left, to the right, or in some random direction, right?
Yes, something like that.
But if you have enough points, let's say, do you need to do that, or wouldn't you just following in something like just normal sampling, like in every iteration, just sampling randomly sample from a uniform distribution?
Yeah, actually, that's a great point. I think my idea in this paper is because PIN is based on gradient, right? You need to calculate the model gradient. So the gradient will be infinitely small. So the perturbation should also be small to guarantee at least in this region, model is well. So if you're sampling in a global region, the distance, even if you have like 10,000 match points, you cannot guarantee a very small interval between collocation points. So the perturbation is a good way to guarantee this. Actually, for the learned perturbation size is quite small. It's like 10 of the power of -4. So it's really small perturbation.
Okay. Thank you for explaining.
Yeah. Keep going. I think I have just described the design of Monte Carlo approximation, that is only sample one point, each region has different iterations. And the second will be the trust region calibration, because Monte Carlo sampling can achieve the region optimization only in expectation. And it also has some gradient estimation error for each iteration because we do the sampling. We do not do the integral. So specifically, the estimation error is equal to the gradient variance within a region. This theorem stated. And let's recall the previous proved generalization bound. It indicates that if you have a larger region size omega r, this can facilitate better generalization. But we cannot unboundedly increase the omega r because it will bring a large gradient estimation error. So therefore, we propose an adaptive strategy to adjust the region size according to the gradient variance among successive iterations. Specifically, in our algorithm, the region size is determined inversely proportional to the gradient variance to enable the training stability. So it's quite intuitive because if you have very unstable gradients, it means the region size is large. So you need to make the region size, you need to reduce the region size to ensure a stable training. And similar ideas is widely used in deep learning optimizers, which involve adopting the optimization statistics to adjust the optimization configuration. And the gradient variance can be easily obtained by retrievaling the computation graph. I mean, for each iteration, you have to conduct a one-time backpropagation for the gradients because you need to do the model update. But we do not need to do the external backpropagation to obtain these gradients. We just do the retrieval. We can retrieve the computation graph and store the gradients in the past several steps, then calculate the gradient variance and further adjust the region size. So this design will not bring extra gradient computation. Therefore, it is comparable to the original point optimization in efficiency. And we also prove that the multi-iteration approximation can also give an accurate estimation of the trust region.
Oh,
so
actually, sorry, I have another question. When you do this, can you go to the previous slide, please? Here, in each step, when you compute this gradient variance for different perturbations of the points, do you fix the parameters during each one of those, or in each step you're also modifying the parameters?
You mean the initial steps training?
Yeah. For example,
yeah, how to calculate the variance.
For example, here, right? You do one forward pass and then you get your XT and then your this part here, right? So when you go to this the next step, you perturb your points, and then you're saying, if I understand correctly, that you're going to compute your variance along this direction, like
yes,
like
yes,
that, right?
yes.
Yeah. So in each step, in each blue line, are you updating your network parameters so the networks are being updated from here to here, or?
Actually, they will update. It's just like a plugin to the original optimization process. It's just like that.
Oh, okay, but in that case, especially at the beginning of training, I mean, these variants will be somehow like too noisy because you don't have any guarantee that they're going to, Yeah,
actually, we do not, for the first 30 iterations, we do not do this strategy. For that, we choose as this strategy. I also try to, for example, for the first 5 steps, we started doing this strategy. It's also stable, but I think it depends on it because for the deep learning neural network, you have to train a lot of hyperparameters, right? So I think that is acceptable. The begin iteration is still a hyperparameter to be trained.
Oh, okay, that's nice. Thank you.
Okay, and so we prove that it's a multi-iteration approximation. You use the multi-iterations model parameter to approximate the gradient estimation error is also accurate. There is a theorem to guarantee this. So in the end, we give the generalization bound for the ridge optimization in practice. Actually, this is the exact generalization bound for RoPINN sample algorithm. Just looking at this equation because other equation is quite common. We can observe that introducing a region can bring 2 inversely proportional terms to the generalization bound, where the generalization is proportional to the region size, and the optimization stability is inversely proportional to this. So it means if you increase the region size, model can take some benefits from the region optimization, but it also has some risk to suffer from the optimization and stability. Well, if you think about the previous point optimization paradigm, you can find that this paradigm is corresponding to an extreme case, which is omega r is equal to 0. And the RoPINN actually provide a more general framework to adaptively balance the optimization and generalization during training. Okay. So here is an intuitive understanding. For the canonical point optimization, we only calculate the gradient on the fixed collocation point in all iterations. And as for the RoPINN, the collocation point of each iteration is slightly shifted within a region like this. So we want to approximate the region optimization by accumulating gradients from multiple iterations. And we also test our proposed RoPINN in extensive benchmarks covering 5 base models, including Transformer and CAN, as well as 19 different PDE tasks. RoPINN can successfully boost diverse base models in extensive BTEs. So if RoPINN can bring a positive promotion, I just label it as blue. So the promotion is quite consistent among different base models and different PDE tasks. And it can also help the model to mitigate the failure modes, like in reaction and and we also okay.
One another question. And in this slide, since you're mainly part of the thing that you're proposing is this sampling strategy, did you compare with the other sampling methods, like as you mentioned, RAD or RAD or?
Yes, we have compared with that in our paper, but we do not show the result here. And I think the main contribution in this paper is provide a more general view to understand what the PIN does during the optimization, because there is a trade-off between the generalization and the optimization stability. I think that is the main contribution of RoPINN.
Okay, makes sense. Thank you.
And we also visualize the training log of RoPINN, which brings very interesting findings. Firstly, as shown in the left side, x-axis is training iterations. The y-axis is the region size. So we analyze the region size change during the optimization. And different curves correspond to different initialization of the region size. You observe that during training, the region size from different initializations will gradually converge to a similar value. This indicates that there is an underlying balance point between optimization and generalization. And the RoPINN can adaptively find the balanced region size and help the convergence. Okay, further, if we sample more points in each region, like the blue one is sample 5 points in each region, and the black one is sample 1 point in each region, we can find that if we sampling more points, because it will give us a more robust estimation of the region gradient, the final region size will be getting larger, and the performance will getting better. So in conclusion, sampling more points will enable better stability and lead to a larger region size. And from the loss landscape visualization, we can also find that RoPINN can be added to the vanilla PIN and help the model to have smooth optimization landscape. And here are some showcases of RoPINN. This is the results for adding RoPINN to PIN. The error is significantly reduced, and the RoPINN can also boost the previous very advanced model Transformer. Okay, that is the first work, RoPINN. We build a region optimization theory and a practical algorithm for optimization. During the proof process, the theory of RoPINN, we obtain additional insight. Actually, this is from the derivation process of the theory. And this helps us to develop the next work, ProPINN. I don't want to talk too much about the proof details and only give an overview about the whole proof process to present an intuitive understanding. Actually, the generalization error be bounded by a term related to the gradient correlation among different collocation points. So the region optimization, because we just extend the region size, so it may be more possible to give a correlated gradient correlation and bring better generalization. So this insight inspires to think about this question. So what will happen if a different collocation point has irrelevant gradients? There comes the ProPINN work. whose title is ProPINN, Demystifying the Propagation Failure in Physics-Informed Neural Networks. And in this work, we established a new theory to explain the propagation failure phenomenon and proposed a new model architecture. Let's start with a peculiar phenomenon in PIN's optimization, which was pointed out by researchers in Virginia Tech and UPenn. And here is an example of the equation. The left is the ground truth. The middle shows the prediction results. And we can observe that these two physics fields are quite different. However, if you check the PIN loss, especially the equation residual term, you can find that the higher error zone has extremely lower residual loss. And this finding indicates that in some cases, the lower PIN loss does not necessarily reflect the accuracy of the solution. And the paper proposed a propagation hypothesis because in most cases, only initial condition and boundary condition have the correct supervision of the solution values. They are lying here and here. So they argue that to avoid the converging to trivial solutions, the internal points, the correct solution must be propagated from the initial point and the boundary points to the internal space. And they give an intuitive explanation about the propagation failure. That is, some collocation points start converging before the correct solution has reached there. So this is quite an intuitive understanding and makes sense. However, we notice a counterexample for this explanation. Consider the FEM finite element methods. These classical numerical methods started from a very trivial estimation. There are internal areas for the incorrect output supervision during the beginning stage. And while PIN suffers from the propagation failure in some cases, but FEM does not. So why this happens? If we take a close look of the technical design of these two methods, you can find a difference. Basically, the solution value, like this, the correlation is quite explicit because it just use the shape function to model the correlations. And actually, if you think about the pins, the correlation is quite implicit. If you want to if you consider the effect process like this, we firstly update the model parameter based on the gradient at position I. And the updated model parameter will affect the value at position xj. So it is an implicit correlation between different points. So based on some basic knowledge of FEMs, we can obtain a propagation paradigm, which is defined as here. And the function D is the explicit correlation between two positions. So we can find that because there is a shape function, EM is under active propagation. And actually, D has very rich physics meaning. Actually, I'm not an expert at physics, but I think you are more familiar than me about this concept. So if we consider the solid mechanicals, D refers to the stiffness matrix, which is the force on the Jth node to make the region balance when Ith node has a unit displacement. And I come up with a question. So let's see what is the stiffness matrix looks like in pins. Since the correlation among different positions in pin is implicit, the change of the solution value only achieved updating the parameter. So we define the matrix from a gradient perspective, which is highlighted in red. Actually, this definition reflects the effect on S prime when we make an optimization step based on the gradient as X, which is defined as here. Eventually, we got a very essential factor, which is denoted by DPIN. And similar to the stiffness matrix, a lower DPIN indicates a weak propagation. That means you cannot propagate the information from this point to this point. Going further, if we expand the definition of DPIN, we can find the necessary and sufficient condition of propagation failure, which is a smaller gradient correlation. That's exactly what we want to know in the previous theory in RoPINN. Okay, actually, this theorem also explains why PIN cannot benefit from large models in some. This is because a large model will have a large parameter size, space, and the high-dimensional gradients are more likely to be orthogonal. This is the basic knowledge of the high-dimensional statistics. Okay, although the about derivative seems complex, it's highly related to a common concept in deep learning, which is overfitting. So if we consider the collocation points, the different data samples, and the representation for nearby points be irrelevant if the model has too strong fitting capability. So that is the overfitting definition. So it means if the model is too strong, it can make the optimization process overfitting a very weird manifold and make the model cannot propagate from the initial points and boundary points to internal points. Okay, here is a visualization. The left is the ground truth, and the second column is the error map, and the third is the PDE residual loss. You can find that the residual loss is very small in many high error zones. But in the last column, we show the region gradient correlation during optimization. Darker color indicates a lower value. So this represents a worse propagation. You can find that the gradient correlation can be a very accurate criterion for the blocked area, because you can see the area is getting worse in this line, and the gradient correlation just highlight this line, so a lower value. So this means gradient correlation is a good criterion to identify which area is propagation field. Okay, that is about theoretical part. Next, we ensure a higher correlation for active propagation and propose the ProPINN. So the ProPINN is actually based on a very simple and efficient multi-scale mixing mechanism. It just mixes the representations of different collocation points within a multi-scale regions. So this is a very convenient way to ensure the explicit correlation among different collocation points. And recently, there also have some transformer-based models. I think you also mentioned something like diffusion DeepONet. Maybe they are targeted on a different objective, that is modeling the spatial temporal correlations. And they implicitly have already achieved a better correlation. I think that maybe that is a fact can account for their better performance. And we theoretically prove that our design in multi-scale mixing can bring a larger gradient correlation for better correlation. And here are some visualizations. Okay.
It's really interesting. First of all, especially the metric that you found. But can you explain a little bit more how this architecture works, because I don't follow it that well.
Okay. For the vanilla PIN, the input will be only one coordinate, right?
Yeah.
I think so. The input is only one coordinate, and the output will be the value at this coordinate. So in ProPINN, we do the random perturbation to augment the input like this. This is a differential perturbation. And we just forward the augmented representations into a very into a shared propagation layer. This is just an MLP. So we got the representation for different points within a region, and then we do the average pooling to obtain this point and the region representation and the latter region representation. So we do MLP on these different multi-scale representations to generate the final result. So if you think, I don't know how to.
So I also see that when you say differential perturbation. So you say point rate region 1, region 2. So each one has like different points, like if different number of points, because for example.
Yes, and they have different region size.
Okay,
so it's multi-scale.
But when you feed it to your shared projection, to your MLP or whatever you're using in there, you can only process one point at a time, right?
Yes, but you augment. This is something like data augmentation. You do the augmentation. The input is still one point. The output is still the value at that point. But you do the augmentation. And the model will inform with the representation with its nearby regions. And if you consider another point that is quite near to X, that's like says S prime, and X is a target point. So because you're mixing the region representations, the region for X and the region for S prime overlap. That is the propagation happens.
Okay, I see. And
Yeah,
maybe this is a conceptual question from my side because I'm trying to understand because it's quite interesting.
yeah, thank you.
When you feed information from the left, like all regard the points that you're putting them, even if you make this as more perturbation, they're still inside they're still inside your domain in some sense, right? Like
Yes,
the x plus delta
yes,
one still lives in your omega.
yes.
Would you get it like a similar effect if, for example, you just have like a really dense set of collocation points and then you do your some type of local convolution in the output and then compute the residuals on that local convolution? Because somehow like looks
Mhm.
similar to what you're doing with this.
Yeah, actually, I think it previously also mentioned the dense collocation points, right? Because the sampling is finite. The sampling you cannot get an infinite resolution. What we want to do is to ensure this. Let's think, just think about this. If the model can overfitting like this, if you do not sample a very dense point to bridge the gap between this part to this part, you cannot achieve that, right? And what we want to do is to build an explicit connection between this point and this point. So it can make the propagation very effectively, not based on sampling, because sampling you need to compute more points. That is less efficient.
Yeah, that's true. That's true. Well, if someone may argue in favor of sampling, they may say that you can just have a really small batch and then
Mhm.
move it in every iteration. So ideally, it could be cheaper, but I agree with you.
Yeah, and we also theoretically prove that this architecture can bring larger gradient correlation for better propagations. And here are some visualization of different standard benchmarks. The left, I mean, this part is vanilla pin, and this part is ProPIN. If we compare the gradient correlations, as highlighted as red arrows, you can find that ProPIN is under a very active propagation. They do not suffer from some blocked areas.
One short question. How
Mhm.
expensive is to compute this gradient correlation? Because it looks like it was like a matrix, right? And you have to, in your derivatives with respect to the parameters. So if your network is big, it may be a bit expensive to compute that, right?
That is a great point. That is why we do not use gradient correlation in our loss. We do not add that. We achieve better gradient correlation by nature. Actually, we also compared as like adding a gradient correlation regularization term to the loss function. It works, but it will cost much more GPU memory and more running time. And in this architecture, we only ensure the better correlation based on architecture. We do not need to calculate the gradient correlations. And that experiment result is only for intuitive understanding why it works.
Makes sense. Makes sense.
And here is a visualization of training dynamics. And it's observed that regarding the training loss, both ProPIN and RoPIN can achieve a lower value. However, the blue curve, which corresponds to the vanilla pin, is really easy to get stuck due to the propagation feeder if we consider the test law. And with active propagation, ProPIN can also support the simulation best dynamics. Here is an example of fluid dynamics. The model is required to solve the dynamics for the future 10 seconds. You can find that the ProPIN can achieve a much lower propagation prediction error, the second best model. And also, as mentioned before, a larger model will more likely to cause orthogonal gradients, resulting in a propagation failure and overfitting. So, however, ProPIN can keep active propagation between different positions. So when we keep ending the layers, ProPIN can still achieve better performance. That means ProPIN can benefit from the scaling during the model size. Okay, and okay, that is our design improving pins. I think pin is a very good formalization, but just like the deep learning, just like deep neural network, when the first proposed was deep neural network, it doesn't work. But we need to add a lot of features like the residual learning, or the transformer, or the scaling to make that paradigm works better. So my previous research is mainly focused on how to make pin framework works better. And I do two explorations. The first is RoPIN to improve the optimization. The second is ProPIN to improve the architecture, which can partially solve the underlying issues of pins. And actually, when doing research about pins, because I'm from the machine learning community, also perceive some unsolved bottleneck for this type of framework. If we think about this problem from a machine learning perspective, I think we still need to. I think we still have not completely unlocked the deep learning capacity in pings. Like we cannot scale the model parameter to a billion scale to enable better generalization and accuracy. Maybe we need a general way to scale neural networks. That's like what I attempted to do in the ProPINN. And additionally, we also got some very exciting news of pings in recent months, including the research enabling 3D turbulence. This work is from Yale. Some researchers from NYU, Stanford, and DeepMind, etc., also demonstrated the potential of pings in scientific discovery, which can be used in discovering the unstable singularity within pings. And previously, I also do some explorations, not only to pings, but also on some hybrid data physics solvers and pure data-driven solvers. And we have released a well-organized library with building advanced algorithms and dataset. So if you are interested, you can also this project. Last, I want to thank my advisors and collaborators. That's all. Thank you.
Thank you very much, Haishu.
Thanks, Professor. Any questions?
Haishu, hi, Izhan here. Just a quick question before we end. I don't know if we have time. Uh, I have a question. Basically, you quickly discussed on the scaling, right? So basically, FEM faced the curse of dimensionality as well, right? And struggle with irregular geometries. So basically, I was thinking on the aspect that have you like explored that ProPINN scales to high dimensional PDEs, like let's say 5D Faulkner-Planck equations, something like that, where FEM becomes intractable, but the standard pins also struggle.
Actually, basically speaking, I do not test that. Just test it on some low-dimensional PDEs. But I think in RoPINN, I did some high-dimensional PDEs. I don't know. Maybe it's worth a try.
Right, because I'm trying to explore some work on the Riemannian manifolds actually. So I was just thinking about that can ProPINN's framework extend to PDs on Riemannian manifolds where the metric structure defines neighborhoods? I don't know. Like just a question running on back of my hand right now.
Yeah. I think it's very important to extend things to some irregular geometries. But actually, because I'm completely a machine learning researcher, so when I first read about the Ping's paper, I think it's kind of like a special position embedding. Like you just input the coordinate and then learn the feature about this coordinate, project the position into a feature. So if we think about the irregular geometries, why it is hard to achieve? Because this geometry will rely on a very powerful position embedding for this. Actually, there are some papers in visual graphics. They try to embed some very complex geometries, like using nerve or something else. I think they can be useful to handle the irregular geometry.
Maybe Professor George can comment of 2 lines on that. Maybe I don't know. Yeah. Thank you.
Well, about the high dimensions, there are we have published several papers with Jae-Yuan Hu on solving Fokker-Planck in 100,000 dimensions using different types of approaches. So yes, this method can be extended to high dimensions. But I have a question, Haishu, because the failure modes that you presented, I mean, if you use resampling, for example, or use which is equivalent using local weights, they don't appear. But more recently, we have shown that when you use second-order optimizers, none of this appears.
Okay.
So,
I see.
So you don't. So you get with FP64. With FP64 and second-order optimizers, you get spectacular convergence at a lower cost, and you don't need this elaborate scheme. So you actually need to compare your results against that, not the old news. In some sense, when you were doing it, it was current and it was a great idea. And I think this regularization and the smoothing that you do is fine. For high order optimizers, we don't do any of the tricks. We don't. I mean, we could resample, but we don't need to resample. We don't use weights, for example, and we still get one of the papers optimizing the optimizers. But we are revisiting this now, and we see that both Gauss-Newton and quasi-Newton methods, self-scaled, which is a work of a visitor that I have, Jorge Urban, and natural gradient methods, all kind of Gauss-Newton or quasi-Newton flavor. They all work without any of the glitches that you show. So that's observation number one. I don't know how you can explain that. Actually, it would be great, since you come from the optimization perspective, to look at this and say, what is that we're gaining here with these different types of descent? Because there is a second order optimizer called SOAP, which is like Adam, preconditional Adam from Google, and that can also help you to see the differences. We're doing that from the observational perspective, not from the analysis perspective. So it would be extremely useful if you can come in and say, especially since you show something that we also have shown, in fact, Juan, who asked you questions before, namely this trade-off between optimization and generalization. So we have something like a learning theory for pins, we call it, that we show that you really need to train for a very, very long time in order to get to the generalization regime.
Okay.
So it's somewhat similar to Tishby's information bottleneck theory, but not quite. But that actually doesn't even apply to the second order optimizers. It's a very good theory that works for first order optimizers, but something else is going on with second order optimizers. So issues like optimization and generalization may be different, but certainly the way you approach the minima, and of course you need FP64 for this to work, but we don't have this problem. This problem, the advection problem, all these other problems, we don't have them. The multi-scale physics, which will give you this very, very corrugated, rough terrains, landscapes.
Yes. Yeah, I think your professor, your comments are very valuable. And actually, the failure mode, I also do not think they are failure mode anymore, because the paper is about 4 years ago, and currently we definitely has new progress to solve these problems. And when talking about the FP64, actually,
sorry, including a paper that you show from DeepMind, they call it for singularities. They call it high precision pins, and they use the Gauss-Newton. They use a Gauss-Newton method.
Yeah. Actually, the first author is a friend of me.
Okay.
I talked to him, and he also tested the RoPINN, I think. With RoPINN, a higher precision optimizer can further boost the performance. So I think it's just like a deep learning area. Before 10 years ago, I think we do not have Adam. We only have SGD. The exploration at that time is valuable because we just want to optimize the whole framework at different directions. But maybe they are orthogonal. But I think it's really valuable to retest the techniques before the high precision optimizer, based on the new optimizer, to see if they have new promotions after new observation. I think it's valuable.
Yeah, it's very useful, and because we also see that with the second order optimizers, if you use resampling, you will enhance the accuracy. But you're already very, very, very good. That's what I'm saying. You don't encounter the anymore. People have put on the I think that's for you, several papers on like a couple of papers on second order optimizers for you to. I see Elham and then Juan.
I put the paper on the learning on pings, and I put it because something really
learning theory and then optimizers. Maybe you can send this to her. But I'll stop. Maybe other people have a very interesting talk, Haishu. Would like to see that perspective from the other side of the fence.
Thank you so much. So everybody, like a few people in our lab, put the link of a few papers in the chat for double precision setting, second order optimizer, representation, and so on. Okay, do we have any questions for the speaker from the audience? I think we will not get any more questions. Thank you so much for your talk. And thank you everybody for joining us today. I think it's time to close the session and have a great weekend. Bye.
Thank you. Thank you. Bye.